right, so we are working on quadratic methods. Quadratic methods are ways to solve quadratic equations, and there are 4 basic methods for solving quadratic equations. Okay. So what we're going to do today is we're going to summarize those 4 methods. Okay. We'll summarize the ones we've already done, 1 and 2, like we did last time. We're going to be making sort of a study guide. Okay. So I suggest starting on a fresh piece of paper, and each method I'm going to use 1 piece of paper. Okay. Or 2, so we don't scrunch up the examples. Okay, so I'm going to give the method, when you're supposed to use it, how you set it up, the steps to use, and then some examples of using it. I'm going to do that for each of the 4 methods. Okay? So I'm just mentioning that beforehand, so you think, especially in your notes, you're in a way creating a study guide. This will carry you into college algebra. So being able to solve quadratic equations by any of these methods is a big topic in college algebra. Okay? And then using them to make graphs, very important in college algebra. So you want to understand why we're solving them and what solutions mean, which is how we'll finish up today. Okay? So we're going to summarize and review the first 2 methods. The 3rd method, completing the square, we were right at the end of last class. We'll get a little more practice on that, and then we'll introduce the 4th and final method, the quadratic formula. Okay? All right. So the quadratic methods. So there's 4 basic methods. The first method is to solve by factoring. Okay. Now this is the topic of Chapter 9 and 9.4. We practiced our factoring in 9.1 through 9.3, and then solved equations that had quadratic expressions by factoring them. That was 9.4. So you can always go back and review that homework or study guide for that section if you need more practice on this. Okay. I'm going to lay out when we use it, how we set it up, and the steps, a couple of examples that is going to transition us to our next method. So we use this because, let me be specific about this. On the exam, I'm going to tell you, use this method, use this method, use this method. You often have a choice of method you can use, but if you don't use the method the direction tells you to, then you won't get credit for it, because I want to see that you can use all the methods. Moving forward, the further you go in algebra, you get to choose. Okay, so you need to know when you can use them, when they're the best choice, when there's a better choice, when you're not allowed to use it. Okay, so that's important. For now, you need to know all the methods and show them all to me. But all of them, different ones can be used in different times. So solving by factoring, you use that when the quadratic expression is factorable. In 9.4, every one I gave you was factorable all the way down to its linear factors. Okay? But not every quadratic is factorable. So you need other methods if it's not. Now I'm going to put in a little extra here, because there are other methods you can use even when they are factorable. Oftentimes, factoring is the first thing you should ask yourself. Factoring is often the easiest and most efficient way. Some of the factoring you should be able to do in your sleep, like A=1 trinomial or difference of squares or a GCF. Okay? So if it's easily factorable, that should be the most automatic first thing you try. Okay? But if it's not factorable, or what I'm going to add in here, if it's not easily factorable, let's say you've got an A not equal to 1 trinomial. That could be with the big numbers in it. That can be ugly and tedious to factor. So you might choose to use another method. Even though it's factorable, another method would also work, and it might be easier to use another method. But for simple factoring, this is usually the most efficient. Okay? So, but you can only use it when it is factorable. And it's the best choice when you've got an easily factorable one. Okay? So, how do you set it up? If you're going to use solve by factoring, if it is factorable, then your setup requires standard form. Okay? In other words, you set it equal to 0. And if you don't do that, then you can't factor and solve it correctly. So the setup's very important. And then the steps. Now the steps, I'm listing these very specifically for very specific reason. One other thing I love about, that's why I have a math brain, is I love the objectivity of this, meaning that math has certain rules and you don't break the rules. I mean, it's not like other subjects which are often very subjective, which I love to learn about, but sometimes it's hard to learn or to even to teach them because there's a lot of different perspectives and a lot of, some of the liberal arts and all. So, but math is very prescriptive. It has certain rules that you have to follow. So once you know those rules and understand the steps and the order they go in, you can relax into them. They have a rhythm. Nothing unexpected. Okay? So the steps I'm listing are not only the important steps, but they're in the order you should use them in. Now, in math, there's often different ways to approach things. And it can be very creative and elegant. There's often other ways to approach it. But when you're learning the foundations, having a real set, consistent list of steps and the order to use them in is helpful until you get really comfortable with it. And then you start to see the creativity and the beauty in the different approaches. So when I list these steps here, I'm listing these steps in this order for a reason. Okay? They give you a place to launch off from. You get comfortable with this first, and then you launch from there. So the steps are always in this order. First, you must put it in standard form. Okay. Once it's in standard form, because you can't factor until it is, everybody's in the house, then you factor completely. Okay. Using whatever method is required. Okay. There's lots of different factoring methods if it's factorable. The ones you should definitely use this for are for difference of squares, A equal 1 trinomials, GCF, or even a 4-term grouping. I'm going to show one of those. Okay? So factor completely, and then you apply your zero factor property. And that says if you have factors equal to 0, the only way you can get a product of 0 is if one of your factors is equal to 0. It's not impossible to get a product of 0 if that's not true. So you set each factor equal to 0 and solve them. So you apply the zero factor property to the linear factors and solve for x. Solve each of them for x. Solve each for x. Okay. You'll have 2 linear factors, and so you'll get 2 solutions. Now I do emphasize here to the linear factors, because one of our examples we're about to see, you can start off factoring. In fact, you have to. There's not another approach. You have to start off factoring. But then, like towards the end, it's like, wait, but I can't get it all the way down to linear factors. So at that point, you have to switch methods. Okay? Doesn't mean what you did was bad up to that point. It's just to finish it off, you're going to need to use another method. Okay? So you apply the zero factor property. The linear factors then are solved right away, but if there's any nonlinear factors, because everything I gave you in 9.4, you could solve all the way, you could factor all the way to linear factors. There may be cases now where that's not true. So you might have a linear factor, you just go ahead and solve, and another one that's not linear, it's prime, you can't get it any more factored, and you have to use a different method. All right, so examples. All right, so x squared plus 24 equals 11x. I'm going to go ahead and put up 4 examples. They're going to be 4 examples that are pretty basic factoring. So you should, if you're not super efficient with these, something you got to focus on, you got to practice. So let's do 12x squared minus 75 equals 0. Put it in standard form, factor completely, set each factor equal to 0, and solve each little linear factor. Feel free to work with each other. Ask me if you have questions. Call me over. I'm going to start putting the answers up here. Don't just copy down what I'm doing. This is so you can check your work as you go. And let me know if there's, oh, wait, what happened there? Or, yeah, no problem, check. But don't rely on just copying down what I'm putting. This is so you can check. Keep your head down till you got it. Check your work, do the next one. Very common careless mistake in that first one is that in putting it in standard form, you put it in the wrong order. I see this often, like when I gave one like this on that test. That 11x, of course, has to be subtracted, so you move it over, but don't write x squared plus 24 minus 11x. You know, standard form is not only everything on one side, but it's also in ax squared plus bx plus c. Quadratic term first, linear term second, constant third. Factoring that requires the ACB method. Well, you can't use an ACB method until you know what your A, your B, and your C is. In A, B, and C, the order matters. A goes with the quadratic, B goes with the linear, and C is the constant. Have to take out a GCF as your first factoring, but if your GCF is numerical, then it's not linear. It's not a variable factor, it's not a linear factor. You have to take it out to continue factoring, but it's not going to give you a solution. Don't say one of the solutions is 3. 3 equals 0 is nonsense. If there's no x, there's no solution. Let me know, any questions, any problems? How did I get from here to there? Sometimes the trickiest thing is just making sure you put it in standard form correctly. Remember, you want your quadratic to be positive. So if it's already positive where it is, even if it's on the right-hand side, then move everything else over to be with it. And you do not want a negative quadratic term. Okay? So if it's positive, leave it where it is and move everything else to be with it. If it's negative, move it over so that'll make it positive. Okay? But then, because it's easier for the eye to look at, it's fine to flip it over. Your eye might be really tempted to treat this like a difference of squares because a perfect square difference. But what do you actually do to factor it? GCF. Always the first question anyway, so once you take that out, you say, oh, well, I'm done. Those are 2 linear factors. That was a GCF that is linear. It does give you a solution. There's no more exponents, so there's nothing else to factor. What method are we using for this last one? It's already in standard form. Is there an overall GCF? Anything they all have in common? No. Okay. So what method of factoring will we use? Right. We count the terms. We check for GCF first, an overall GCF. There's not one, so now we count terms. 2 terms, we have a binomial. Maybe it's a difference of squares or a sum of difference of cubes. 3 terms, it's a trinomial. Is it a equal 1 or a not equal to 1? Or is it a perfect square trinomial? 4 terms, we use grouping, period. There's not even anything else to ask, like, oh, what kind of trinomial or binomial? Nope, 4 term, you group. There's a plus in the middle, so no worries here, just putting up our groups. What degree was our original equation? Degree 3, because it's cubic. So how many solutions are we expecting? 3. So in order to get those solutions, how many linear factors do we want?
3.
3. Yeah. So far we have 2. The grouping method gave us 2 binomials. This one's done. But this one still has a square, so we should be able to get 2 more out of it, right? So we got to factor this one further. Can we factor this? No. 1, it's not this is a square, but it's not a difference, and that's not a square. Right? This is prime. If I back in chapter 9, if I just gave you the expression, not an equation, the expression said factor it, you'd get there and you'd be done. Now you'd have to ask yourself, oh, can I keep going? There's still a square, and the answer would be no, it's prime. I'm done. But this is an equation, and we are going to get, whether or not we get 3 linear factors, we're still going to get 3 solutions. Okay? So, we still use our 0 factor property. X minus 3 equals 0. And we'll go ahead and set it, so either this is equal to 0 or this one's equal to 0. We can't factor any further, but we can go ahead and say it's still a factor. So either this is equal to 0 or this is. Now this one, no problem, x equals 3. It's just a little linear. Okay. But since this couldn't be factored, we're going to have to use a different method. We will get 2 solutions out of it. It's still a quadratic equation. But we're not going to get them by factoring. Why? What do you do first to solve this?
You subtract 5.
Exactly. Yes. Right now it's technically in standard form, which is what we need for factoring, but it can't be factored, so it has just a quadratic and just a constant. Therefore, we can use the square root property, which means it can't, not in standard form. We put the quadratic on the left and the constant on the right. Square root both sides. Plus or minus square root of negative 5. So x equals, we'll pull out that negative as an I, so plus or negative I square root of 5. Now we have to simplify the radical further if we can. We can't. Okay. And we already solved for x. X is either positive I square root of 5 or negative I square root of 5. So here's one solution, and here's 2 more solutions. For a total of 3 solutions. One of our solutions is real. And one of our the other 2 solutions were imaginary, non-real. So when we write our answer, 3, comma, negative I radical 5, positive I radical 5. 3 solutions, 1 real and 2 imaginary. There's no other approach to solving this one except to start factoring, 4-term factoring. And that got us mostly there, but we had to finish off with a different method. If you hit a prime factor, then you're going to have to solve it probably by the square root property. Or even something else. It depends. For our purposes, this is the most decision you'd have to make. But there may be other options as we get more and more complex as you move into other higher algebras. So good with this? Okay. All right, so solve by factoring. So I'm going to put that's study guide for one method. Method 2. That transitions us into the second method, solve with square root property. And this was from 12.1. So we use this when you have only a quadratic term and a constant. Okay? In other words, there's no linear term. So it's very specific. This is a very specific method. It won't solve any quadratic. It'll only solve a quadratic equation where you only have a quadratic term and a constant. And, another thing, so use when you have only a quadratic term and a constant, and the expression is not factorable. It's funny how the brain works, but that actually confuse things. So, is not factorable. Now, you can actually use this method if it is factorable. It's just, if it's factorable, it's probably just going to be a little difference of squares. It's easier just to deal with, generally easier to deal with factoring it. Okay. So you can actually use it for any quadratic equation that has just a quadratic term and a constant with no linear, whether it's factorable or not. But the best time to use it is when you're kind of stuck because you have a quadratic that's not a difference of squares. Okay, so the setup, unlike with factoring where the setup is standard form, you set it up to be either x squared equal to c, or if you're dealing with a binomial squared, it'll be a binomial squared equal to c. So not in standard form. Now, in words, this means you have a quadratic term, I'm abbreviating there, quad term, or a binomial squared, I'm going to abbreviate that too. So you have a quadratic term or a binomial squared. Okay. The quadratic or binomial squared is, and I put this in quotes because, like I told you last time, it's not a technical math term. It's naked and alone. Okay. So there's no coefficient in front of it, and there's nothing being added or subtracted to it. Naked and alone, nothing added or subtracted, no coefficient. Okay. So, and that's on, I'll abbreviate this, LH, that means left-hand side. So that there's a quadratic term or a binomial squared that is naked and alone on the left-hand side, and the constant is alone on the right-hand side. Alone on the right-hand side. Okay. That's the setup, both in algebraic and in words. Okay. So, your steps. One, put in the above form. If you don't do this first, everything else after that will be wrong. Okay. Okay. When it's in that above form, with the quadratic naked and alone on the left and the constant on the right, or the binomial squared naked and alone on the left and the constant on the right, then you square root both sides. That's the square root property. Now I'll give a little algebraic way that looks. If you start off with x squared equals c, you square root both sides. And that means putting the plus minus in front of the right-hand side because you're looking for two solutions, and either a positive or negative version would make this true, would satisfy the equation. That, of course, gives you an x on the left and positive negative radical c, which you would then simplify if possible. Bless you. And if you have a binomial squared equal to c, you also square root both sides with a positive negative in front of the c on the right, and that releases ax squared plus b on the left equals positive negative square root of c. And you have to simplify the radical and then solve for x. Okay. So when you square root both sides, that's the result you get. And from there, first, a lot of people, you don't have to do this one first. I suggest it strongly in this order because I want you to get into consistent order. A lot of times if you don't do this one next, you forget to do it before you walk away. So after you square root both sides, your first job should be to simplify the radical. Simplify the radical completely if possible. If it's a perfect square, it gets rooted and released. If it's imaginary, you pull the I out. If it's not a perfect square, but it can be partially simplified, you do that, so you still have a leftover bit. Whatever needs to be done to simplify that radical. And then finally, if you started with a binomial squared, using the second version here, then you have to finish solving for x. Here, if you start with just an x squared and naked x squared on the left, then you simplify the radical and you're done because you already solved for x. If you start with the binomial squared, after you simplify the radical, you'll have to finish solving for x. You'll have to, add the opposite to b to the other side and then divide away the a. So finish solving for x. And examples. Now in this case, I'm going to do 2 examples on the bottom of my page, however you space yourself. I tried to do 4 in my first class and got real scrunched up with the answers and all. So I'm going to do 2 here, and then I'll do 2 on the back or on the next page. So examples, we'll start with x squared plus 81 equals 0, and also 3x squared equals 36. You note that you have just a quadratic and a constant, just a quadratic and a constant. And because of the numbers involved, your eye might first instinctually say, oh, maybe I can factor those. But once you clean them up and everything, you'll say, well, already, that would be a sum of squares, so no. It's like, 36, yeah, but 3's not, so I might have to take out a GCF, and then we'll see if I can factor it from there. Or if the directions just say solve using the square root property, which they will right now, because I'm going to have you show me every method. So I have to put it in the proper form. Go from there. So simplifying the radical, if it's negative, pull out that I first and then see what you have left and see if it's either a perfect square or a partial perfect square. Square root of 81. Is a perfect square, so it gets rooted and released entirely. No radical left, no leftover bits.